Today I'm going to talk about time series modeling for demand forecasting, starting from the traditional Max, random forests, which we use a lot, and then transformers, and then end with some, prompt engineering anecdotes, because that's what we've been hearing about all these days, last few months, last couple of years. Right. So the agenda for today is as follows. So I'll start with a brief history of time series forecasting models. It's more like an overview than a history. And then I will go on to a particular case study on some of the demand forecasting work that we did at Sortly, where I consult on AI. And finally, we'll have some, these prompt engineering anecdotes that I talked about. Okay, so let's get started. This is the first part. So brief history of time series modeling for demand forecasting. So why demand forecasting, right? So demand forecasting is basically, for those of you who have not done much with it, the idea is, okay, you look at the past demand, or let's say you're an e-commerce store. You look at what people bought the last few days or weeks and so on, the past history of what people bought, and try to predict how much people will buy, right? And it has a lot of applications for inventory management, out of stock prediction, overstock mitigation, and so on. You can do production planning, pricing, and promotion planning, capacity planning, risk management, and there are a lot of applications for demand forecasting. So when you talk about a brief history of demand forecasting, demand forecasting has a very long history, as you can see here. So those are all demand forecasting models that people came up with. So this is again a very brief history, not very deep history, given our time constraints. So what I'll do is, instead of going over all these models, which will be maybe a chapter in a PhD thesis or something, which we can't cover today. So what I'll do instead is, I want to put them in 3 different buckets, most of these models. So first we have, the decomposable time series models is what I'm calling the first bucket. So these type of models try to break down the time series into the constituent parts, right? For instance, a time series will have trend, seasonality, a bunch of different characteristics that are common across time series. And these models try to explicitly model these features of these characteristics of the time series. Examples of these models are a RIMA model, Max model, or the more recent Profit model by Facebook. So the second set of models is a lot of people though have taken a hack of using our classical machine learning approaches, such as random forests, for example, treating time series forecasting as a regression problem and throwing in a lot of features that capture all these characteristics of time series data. So for example, suppose time series has trend, seasonality, and so on, right? So you give features like, day of the week of the month, and so on to your random forest model. And then you can capture some of those aspects when you actually model it this way, right? So that's the second bucket of models. And the reason we are even talking about them, though that's not the most principled way of doing it, it actually works a lot and a lot of people end up using it. So we are still talking about that, right? And the third bucket is deep learning based models that have been relatively more recent. There are lot of different models, right, from your recurrent neural networks to more recently attention based models, right? So these are the 3 big buckets. And then there are a lot of models that, combine some of these things as well, right? And in fact, if I ask ChatGPT here, can you tell me, a one-liner about these 3 approaches? So I just fed it the slide and asked it for a one-liner, and it gave a really nice analogy. So the ARIMA, Max, and all these decomposable time series models are like the reliable grandpa ends of time series forecasting. So if you've seen Lord of the Rings, so there are these huge trees which are very conservative, very traditional, and they don't change their opinion, and they've been there for thousands of years. So these are the ends that you saw in Lord of the Rings, right? And they do work well for things that fit those parameters, for workloads that fit that parameters. Then there are these ensemble models. They're like Avengers of forecasting, combining powers to save the day, and somehow they, sort of make it work. And then you have the third bucket, the transformer-based models. These are time series wizards casting spells with attention and reshaping the future. So if you're a fan of Avengers, that's like maybe Doctor Who, right? So they have some mystic powers, and they actually do very well on a lot of the tasks. But sometimes, understanding how they work, interpretability could be a challenge, but they actually perform really well on a lot of tasks. So that's like, a brief gist of, one thing you can take away from this talk today. So now let's dig one level deeper into each of these. So if you look at a typical time series, if you try to look at the time series data, the first graph here is like, the observed time series, graph. And the second one is actually the trend. So this is a decomposition of the time series where you're seeing the trend, the seasonality. And then if you remove the trend and seasonality, you're seeing like the residual, right? So this shows you like, you can see some weekly seasonality here, right? This is actually some data from Sortly where I work with, right? So there is weekly seasonality here. If you remove that, then you can actually see that small peaks that you see in the first graph are gone, and you can see like, just the trend. And then if you remove both these, you see the residuals, which is like a bit like a noise here. And then you see like an anomaly that is there in between and so on, right? Okay. So now the first bucket of models, right? These decomposable time series models, what they do is they actually try to look at this trend, seasonality, and so on. And they try to write the model as a combination of all these things. Just like in the picture you have seen, they also have like, terms in the models that they are adding up here. Right, so they have a term for different, previous lag terms, which is like something called autoregression. So they try to capture the trend, the seasonality, and so on explicitly by having some terms in the model, right? And it could be additive, and there are some more recent things that are multiplicative as well. The nice thing is that there is a very explicit interpretation for what this model is doing, right? So that's the good part. So we know that, it's capturing the seasonality, and we have already done some analysis. We know what seasonality our plots have, and we are giving that to a model. We might anyway do this analysis, but these are like very a principled way of approaching it, right? And they perform well when data has strong characteristics of trend, seasonality, and all these things that the model tries to capture, right? The not so great about these models is sometimes it is harder to work with these explicit characteristics, and not everything actually fits that model of, there are a lot of more eccentric characteristics of some of the time series data that we see, which might not fit in this bucket. And that's one thing that, where they fall short sometimes. Okay. So the second is, like the random forest kind of models. And these models actually, for many of the smaller problems, they actually work pretty well. And a lot of people use them in practice. If your problem space is not too complex, and like you have small data sets, especially which you want to train, then the random forest model works in a lot of cases. But the challenge with these models is that, you can give them a lot of features to capture your understanding of the real world. Right? Or this is like light GBM or XG boost. So these are all like variants that you would use. And the challenge here is, it requires extensive feature engineering. So you need to be like, really careful about what features you're coming up with. And the model is as good as the data and the features, right? And of course, it is a bit of a black box, but then you have all these ways to interpret. For example, at least you can get things like feature importances, right? So at least it is a bit interpretable in that terms, right? And it's actually quite, these models are quite simple, at least like some of them. The third bucket is like, deep learning based models. The traditional models that we used here are like recurrent neural networks, GRUs, LSTMs. And more recently, people have been using like, self-attention, transformer-based models and so on. So if you look at these, GRUs and LSTMs, recurrent neural networks, you're actually, in the traditional days, you're looking at one input point at a time. And if you look at the model, the way it works is, okay, there is, at any point of time, you're looking at one new input, And then everything that you learned about the sequence so far is carried over in some hidden state, the green box there. And then, when you go to the next input, you look at the previous green box, which is like a summary of everything you have seen, plus the new input, right? So that's how they work. And because of that, they cannot capture very long range dependencies because all the previous history has been condensed into, one small green box there, right? And then, this architecture evolved. And we have, the latest is, self-attention, which just where there is visibility across the entire sequence when, the model is looking at the entire sequence to train to understand very long-term dependencies, right? Well, you predict, though, you have to do one at a time. So that's like, a very, again, good thing is they can actually capture very complex dependencies. And of course, the bad is that sometimes it's not very interpretable. And sometimes you end up with a lot of parameters for these models. So you need to fine tune them carefully. So that's the challenge with these, if any of you have used them, right? So this is like, a very, very high level overview of the different buckets or the different types of time series models. And most of them fall in one of these. Some of them are like, an intersection of a few of them, right? Okay. So the next part is a brief overview of some demand forecasting work that I've done at Sortly, which is, I'll tell you a little bit more about this company. Sortly is an inventory management software. So what it does is it's like a Dropbox for inventory management where you can actually just, move things from one folder to another to indicate a change of status or a change of location of that object, right? So it's as simple as that. And it is something that can be used in a lot of different use cases. So the customers of Sortly are very diverse, right? From, someone who's an interior designer to someone who's a tattoo artist, a tattoo studio. We have like, very diverse set of customers and hence very diverse set of workflows. So if I'm in a company like, an e-commerce company, like say Amazon or Flipkart, I know the kind of workloads that I have, right? And I know their characteristics a bit, but at Sortly, we have such diverse workloads that, we want to predict demand, but it cannot be tailored to a particular kind of workload here, right? That's the challenge we have. And if I show you, again, the demand forecasting problem here is very simple. So I have the transaction history, which means if I take a particular item, I know when I increased its quantity, when I reduced its quantity. That's what I know, right? Like think of putting stuff in a folder and taking stuff away from a folder. So all I know is the transactions on that item. And now what I want is the demand in the next X days. So can I give an estimate of how many items will be consumed in the next 14 days, let's say, right? Or 28 days or 7 days. So that's the challenge here. And again, it's hard because we don't know a lot about the kind of workloads that we have. So apart from that, the data also has actually a lot of anomalies. So let me show you that. This is an example. So as you can see, the data is actually weekly, but the anomalies are, the outliers are like, such high outliers, like the outliers go to 3,000 while the data is actually like, less than 50 or something usually. The mean value of the data is very low, but the outliers are really putting things off here. And that's pretty common in these workloads. It could be for a lot of reasons, like mistakes when people are doing stuff to like, unseen things that are happening, right? So this is a challenge, and you can actually also see like a weekly spend pattern here. So we won't spend time on that. Yeah, so this is another example where you have like two different kinds of outliers. The first outliers that you see are like, a peak because of a Christmas peak. So you see like, the demand going up in December 2021, right? That's probably because of some kind of a Christmas, peak. And then you see again, another kind of a peak in December of 2022, right? So that is maybe something we can predict, right? But there is another peak in between, the anomaly, which we can't predict. Right. So anyway, these are all challenges when we actually try to forecast. You could call this a form of long-term dependency, though it's also like, we could call it seasonality, but like this is also an example of a long-term dependency, the Christmas peak, right? Okay. So another problem, like, another thing that you see here is in December 2021, you see like an out of stock problem for this particular node. What you see is the consumption is 0 for a while, and that's because it was out of stock. But that's learning the wrong thing about the demand there, right? Especially if I don't have the inventory signal. Sometimes it's challenging to see what's happening. So I'm seeing like a lot of zeros there. So it might end up learning the wrong thing as well. Right? So these are all some challenges that we have to deal with when we actually want to predict in this kind of situation. So now I don't think we have a lot of time. So I'm going to like very quickly go over the rest. Okay. So I'm just going to show like, I'm just going to show some results that some of the models that we have tried. Okay. So we tried like a Serimax model. So we tried a lot more models, but I'm just like, putting one from each of the bucket that I talked about sort of to make it more feasible here. So Serimax, random forest, and, a transformer based model. And GRU also, because I call them like, different types. So what we see is, the transformer is performing well, and there are different nodes. So the thing that's measured here is called mean average percentage error. The lower, the better. And what we see overall is that there are many challenges like capturing long-term dependencies. So GRU may not be able to capture that 1-year dependency, for example, unless I give that explicitly as a feature. So because of various characteristics, which I don't want to go into now, given our constraints of time, we see that, like different models do well in different situations. The models that have like, a nice trend and periodicity, right? The Serimax model is doing pretty well actually. And I picked like 3 different types of nodes actually. That's one of the, yeah. And this is the transformer architecture. I'm going to skip this now. Okay, so but the point to take away here is, the idea is not to look at this table and just pick that which is like doing the best. That's usually not the only criterion. So when you're actually trying to pick a model in a real production environment, you look at a lot of different things, like how well the model works. That's definitely one aspect. But you also want to see, how simple the model is. So if you have like a really simple model, like a random forest is getting to 90% of what the other model is doing, and if it's good enough for your application, then maybe that's like, much more tractable to work with, right? So that's a consideration. Interpretability of the model. So if something goes wrong, or like, you want to understand why something is happening, right? When a model predicts a high demand, you understand why that's happening is useful sometimes. Or if there is a bug and it's definitely interpretable, models are easier to problem solve. Then feature engineering effort, runtime scalability, and so on, right? So you want to look at all these things when you're picking a model. Okay. So with this, I just want to like, I'm almost done here. So I thought I'll just take like a few minutes to talk about, some prompt engineering stories when I was like, working on this project, when our team was working on this project. So, yeah, so I don't think we have a lot of time. So I'll just go over like, what are all the different kind of things for which prompt engineering could be used here? And what are some observations or things to keep in mind or takeaways? So I'll just do those two things and, sort of skip over the other things right now. So we can quickly write prototype code end to end. So if I want to do like a Serimax model with a certain kind of input, then I would give the input format and, I can actually give a detailed function like this, like this is the input and, write a function. And it could actually write the entire code for you, right? So that could be very useful if you want to prototype something specially. But then once you do it, you have to review it very thoroughly, run it through a lot of test cases and so on, right? Generating test data sets. So this is like really, you want to generate these baby data sets to test and even want to put in your pipeline maybe to see if, on a recurring basis, if things are working well. And I can generate different kinds of data sets very easily with, this kind of with LLMs. Ask the LLM to check for a problem. So for instance, sometimes, an intern writes a code, then I sometimes copy paste the code and ask, do you see any data leakages here? While I am reviewing the code, data leakages, for example, is one of the things that's really scary to a data scientist, because you think everything is working and then actually boom, when it hits production, it doesn't, right? So you can actually ask, and while you do review it, it will give you pointers, like this is where you might want to check, this is where you might want to check. And I found that really helpful. right? Model debugging, right? Something is not working well. So like, my model is not giving enough weightage to local fluctuations. What can I change in my model? And I paste the code, right? So it will say parameter name, argument. It will just take the exact variable name and it will say, you might want to change this variable. You might want to give more weightage to this variable in your code and so on, right? Makes it very easy for me as a data scientist. Ask the LLM to refactor code. So it doesn't do a great job maybe, but it does definitely, if you give it more inputs like, what you want your major classes to be or functions to be, then it does a reasonable job of refactoring it that way. And again, when you ask LLM to do something with your code, you have to thoroughly test it and review it. Then suppose you're changing platforms, like I'm writing something on, let's say, doing some prototype on Google Colab, and I want to go to like a SageMaker notebook with different ways it's reading input and so on. So I just ask it to, give the endpoints and like, give it everything and say, okay, convert my code into a SageMaker notebook. So it does the Boto, everything, and you get code. Right? So a lot of ways in which I personally found it useful in the last few months. And I thought this is useful to share. Something all of you might have figured out as well, but I thought it's always nice to, given this is a networking session, I thought this is, something nice for people to look at. And then the last thing, right? Yeah, I think, but some things to keep in mind when we are actually using LLMs for generating code is that it's often very iterative. You need to figure out the right prompt, and sometimes, you can give do an iterative understanding of what prompt works and then give a very detailed prompt. So an example of a detailed prompt was, this is an example of a detailed prompt where it generated the entire program. But to get into this details, definitely I had to do a lot of iterative stuff, and it has like a lot of understanding that a data scientist has about the program to come up with the detailed prompt. But then, it is a little more bug-free than, let's say, an intern going and writing the same code maybe sometimes. Then sometimes, whatever it might come up might not be the best architecture, like it might over-engineer something. It might have like, if you're asking it to design a deep neural network, it might have a lot of layers that you don't want. So it doesn't know your data yet as of now today. So you might want to, check that and prune it and get the smallest network you want, or like, make it more complex, add more layers if you think it's not working well enough and so on. You will have to do that. Sometimes it could miss some steps, like, it might not scale your data, or it might not do certain things that you want to do. So you need to, iteratively figure out and tell it. Sometimes it hallucinates, of course. That's something you can, you have to live with right now. So that's about what I have today. I hope I've not exceeded my time too much. We're good? Okay. Sure. What's that?
What's data leakage? I'm not a data.
What's data?
Leakage, you said, right?
Data leakage. Yeah. Okay. So data leakage is when you're training a model, right? You have the entire training data set to look at. But when you're actually going to use it in production, especially like take a time series setting, let's say you're going to predict the demand for the next 1 week. I do not know the next 1 week sales data, right? If I knew it, I would not be predicting demand. But in your training, when you're training your model, right, you actually have the future values. So sometimes what happens is we end up making some, mistakes by letting the model understand what's in the future. As an example, let's say I am trying to normalize my data, right? I'm scaling my data depending on the largest value in the data. So if I take my train data and scale it according to that, then, okay, I am supposed to know the values of train data anyway. But if I actually scale my test data when I'm actually testing my model with other points in the test data, it means I'm looking at a future point to know like the maximum, right? So that's an example of data leakage. So I know that, okay, it's going to go very high at some point, which the model is not supposed to until, right? So that's an example of data leakage. And it's very common and it's very subtle, and even like experienced data scientists sometimes end up doing it.
Hi. So you said you generated test data sets using GPT. So how reliable is it, and like what kind of variations does it show? Because you want to make sure that the test data set is like a good sample. How do you make sure that happens?
I mean, there are two things. You can, of course, ask an LLM what kind of test data sets for this problem, but typically the test data sets, you will have some domain knowledge and you know that, okay, what are the challenges that my data has? So if I'm looking at the data that I have, okay, I want to, generate a data set with seasonality, right? Which has like a weekly pattern. I can do that, right? I can even do like a small sinusoidal thing. Though that is not like realistically, it might not be sinusoidal, but just, just something that is has a constant frequency, right? Or I could do something with a constant trend and so on, right? So like, that's simple examples. And if you know more interesting characteristics of your data, you can try to make it generate small data sets of like, maybe small tractable data sets that you can actually put in your pipeline so that every time you run your model, it runs on them. And then you see if the results are what you expect, right? So it's like a test case, it becomes like a test case.